Right, we're going to prove that a parameterized surface is locally a map part 2 theorem. Now, what are our assumptions? Well, let phi be a map mapping some subset of the k-dimensional real space into the n-dimensional real space. Phi be smooth. U0 be some subset of U, and B open and bounded. Moreover, let the closure of U0 be also a subset of U, the rank of the vector derivative or Jacobian of phi at U be equal to k. In other words, it is a full rank for all U in is it's not full rank, it's the largest possible rank, because we're not dealing with the square matrix. For all U in U0. And finally, let phi be invertible on U0 and the intersection of the image of U0 and the boundary of U0 be the empty set. Then phi restricted to U0 is a k-chart. How do we go on? How we go on about proving this? Well, we're going to lead the proof by contradiction. So we need to show what we have to show that phi restricted to U0 is a k-chart is that phi is a homeomorphism when restricted to U0, and this means that it has a continuous, well, first of all, that it is continuous, but we assume it is smooth, so that's already out of the way, but also that its inverse is continuous. And that's not so clear, but we shall see that the proof is trivial. Now, we need to show, or we need to show phi is a homeomorphism. That is, that phi inverse is continuous. Well, assume it is not so. So assume the converse. This means by the Heinous Theorem, so by the Heinous Theorem, this means that, and of course the Heinous Theorem is an equivalent, so we are going to, well, it's clear what we're going to do. By the Heinous Theorem, if it is not continuous, it means that there exists some sequence phi, well, rather some sequence ui, it's ranging through 1 to infinity, such that phi of ui approaches phi u 0 and where u, I, and u are from the set capital U0, and that ui does not converge to U0. This is equivalent to saying that the phi inverse of phi of ui does not converge to phi inverse of phi of U0. So one can see indeed that I am using the Heinous Theorem. Well, fair enough. But we observe that the set capital U closure is compact because it is, well, closed because we're dealing with a closure, and bounded because U is bounded. Then in particular U closure is bounded, is compact. By definition then, there exists a subsequence nk such that U and K converge to some U, say, prime in U0 closure. So, first statement, this is the definition of a compact set, or one of the possible definitions of a compact set. Now, since phi is continuous, it is smooth, but particularly it is continuous. So since phi is continuous, we have since phi is continuous, we have that phi of u and k by Heinous Theorem again approaches phi of u prime, but at the same time, while phi of u, I have changed the indexing, doesn't matter, un, we could have been using n here as well, and here. But the point is that phi of un k approaches phi of u prime, while phi of un approaches phi of u 0. Well, this in particular means that, so this means, because if one has a convergent sequence, a convergent subsequence must converge to the same value. So this means that phi of u prime is equal to phi of u0. But of course, phi is invertible by assumption. So this means that applying phi inverse on both sides of the equation, we have that u prime is equal to u0. But this is a contradiction because we have assumed that ui or un do not converge to u0. And yet, we have that